All right, everybody, welcome to the start of Chapter 8, Torque and Angular Momentum. All right, so we'll start with our concepts of rotational kinetic energy and rotational inertia, or the moment of inertia of a specific, of an object of a specific geometry. So our rotational kinetic energy is going to be 1/2 I omega squared, where omega, so let's see, omega is still our angular speed or our angular velocity. I is going to be your moment of inertia. So it's going to be these two equations here. We can figure out where this comes from by saying, well, if I look at what I know about kinetic energy so far, we could carry this on to any number of entries. Which means that our kinetic energy for our system is going to be the sum of all the individual kinetic energies. Now, we remember that our linear velocity is going to equal our omega, where r is going to be the radius of a rotating body. Okay, so then when we put that in here, and then for v squared, when you get r squared, omega squared. Okay, now notice that we're still summing over the mass and various radii, but omega is not part of the sum. So let's take a look at why that is. So let's just say we have a rotating object here. I don't know, about right there, should be pretty much close to the center of rotation. Now, let's just imagine we have, let's look at surface area elements at different radii along this rotating object. So let's see, put one there, 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 and let's put one on the very edge. Now, each one of these is going to have a linear velocity. Okay. Now, the velocities will change based off the radius. The linear velocity will change based off the radius that your individual element is at. However, the overall motion of the object itself has one singular angular speed. So that's why we don't sum over the angular speed. So then let's take a look at what we have here. Now, just like an integral, a sum, anything that's a constant can be pulled out of the sum. So let's say our rotational kinetic energy, we're going to pull the 1/2 out. And we'll go ahead and pull the omega out. Which, now what you see here, this is what's known as I, or the moment of inertia of this object. So then your rotational kinetic energy This is where it becomes the 1/2 I omega squared. And then, of course, your moment of inertia becomes the sum of your masses times the square of your radii. Now, every single object that has a specific geometry is going to have a moment of inertia associated with that geometry. Here, for example, we're looking at a solid cylinder. Okay, and pay attention. What we're doing here is we're saying that we're basically looking at individual little hollow cylinders, and we're going to go from the very center of the cylinder all the way out to the edge, one differential little thickness at a time. Okay, so if we start with our moment of inertia, and then we think of this as if we're going to end up summing up each individual tiny differential of the cylinder, what this becomes is an integral. So there's our r squared, and then we're going to put dm in there because you can imagine each one of these infinitely small little cylinders is going to end up making up the entire cylinder. As the radius gets larger and larger and larger, that mass is also the mass of each cylinder we add up is going to grow by an infinitesimal amount. So your dm, your differential of your mass. We remember though, the density of an object is the mass over the volume. So then the mass of the object becomes the density times the volume. And so, of course, density is going to be inherent to the material of the object itself. So what's going to change is as the radius is getting a little bit larger and larger and larger, as we get each differential mass element, we'll have the same density, but the volume will also be increasing by a differential amount. That's going to allow us to then rewrite our integral. Like that. Now, each individual volume element. Okay, so this is a cylinder. So our volume, and imagine these as hollow cylinders with a thickness dr. Okay, so to get the entire to get the entire volume of these hollow cylinders, we're going to have the circumference of the uh, circular part of the cylinder times the length of the cylinder times the thickness. And that'll give us the individual little volume elements. And so that means each dV, the circumference is 2 pi r, the length is L, and then of course the thickness is going to be dr. And you can see that mocked up on the cylinder up here. Okay, now we're going to stick this into our integral. We're going to go ahead and set the integral from 0 to r. So of course, you see r at the very edge of the cylinder. 0 is going to be at the very center. So we're just going to be summing together all these individual little differential cylinder elements from the very center all the way out to r. Alrighty, so, and that means we're going to have r squared. We're going to put our differential volume element in here, which of course rho dv. So we're going to have r squared times rho, then dv is going to be 2 pi L dr. 2 pi r. There we go, 2 pi r. And this is going to give us an integral from 0 to r cubed, the density of the cylinder, 2 pi L dr. Now, you notice that the density, the 2 pi and the L are constants. We can go ahead and pull those up front. And then inside we're going to have r cubed dr. So now the integrals become quite simple. Let's remember that the power rule for integration this comes out to be 1 over n plus 1 x to the n plus 1. And any of you mathematicians out there who are saying, who are banging your head against the wall going, you didn't put in the integration constant. This is an indefinite integral. You forgot the integration constant. It's going to be taken care of because our actual integral is a definite integral. And in your life as a mathematician, you're going to run into a number of physicists who are going to do things that are going to make you want to slam your head in the door. It's just kind of the play back and forth between physicists and pure mathematicians. But let's just say the constant's going to be taken care of in our definite integral here. Okay, so using this formula, what we're going to get, we're going to have rho 2 pi L. So n plus 1, that's 1 over 4. And then r to the fourth, and then we have our limits of integration. 0 to r. It's going to be rho 2 pi L. Oh, let's see. And then we're going to have 1/4 r to the fourth minus 1/4 0. And so this is going to end up becoming 1/4 rho 2 pi L r to the fourth, which we can go ahead and get rid of that 2. So it'll be 1/2 rho pi L r to the fourth. And then we say, well, density is going to be the mass of this cylinder over the cylinder's volume. And for a cylinder, that's going to be mass over pi r squared L. And so we're going to plug this in. Let's see, for our density, 1/2. And then we're going to have pi r squared L m. And then we're going to have pi L r to the fourth. And this ends up reducing down to 1/2 the mass of the cylinder itself multiplied by the maximum radius squared. Okay, so that's just to show you that each individual geometry for an object is going to have a unique moment of inertia. Okay, so, and you could derive any one of them. So here you see your solid cylinder, 1/2 mr squared. But I think it's going to be best just to kind of go through the list. And you're going to notice each one of these individual shapes is going to have its own moment of inertia. So thin, hollow cylindrical shell, a hollow cylindrical shell, or cylindrical or hollow or hollow, a disc with no center, a rectangular plane rotating about its axis, a solid sphere, a hollow sphere. Let's see, thin rod rotating around where the rotation point is at the end of the rod, and then a rotating rod where the rotation is at the center of the rod. Okay, so they're each going to have their own moment of inertia based off the geometry. So in the future, it's probably just easiest to look up the moment of inertia. Since this is an algebra-based course, of course, you won't be doing calculus on exams or assignments, but it just shows you that we don't just pull stuff out of thin air. all of this stuff comes from somewhere. Okay, so continuing on, let's look at an exercise. We all remember merry-go-rounds on the playground. When I was growing up, the merry-go-round was a rite of passage, and you go out for recess, and if you survived, well, you came back in tougher than you were. And we'd rotate them as fast as we could, trying to throw people off the merry-go-round. So essentially, the merry-go-round is a uniform disc that rotates about a vertical axis through its center. Oh, let's see. Okay, so the merry-go-round disc has a radius of 2 meters and a mass of 160 kilograms. Let's say a child of mass 18.4 kilograms sits at the edge of the merry-go-round. What is the merry-go-round's rotational inertia, including the contribution due to the child? Okay, so now we go back up to our list and we say, well, what about our disk? Okay, well, where's our, I guess I didn't put it on there. Okay, so our disk is essentially a very short solid cylinder. So we're going to use a solid cylinder uh, equation. All right. And then the moment of inertia of the child. Well, this one we can look at just the standard equation for moment of inertia. It's going to be the mass of your object at whatever radius it's at squared. We only have one object, so the child, which is just going to be the mass of the child and the radius that the child's at squared. Okay. Your big R and your little r in this case are going to be the same, so I'm just going to end up making those the same. So what we want now is for the moment of inertia of the system, we want the total moment of inertia, which is going to be the sum of all of our moments of inertia. And so that's going to give us the moment of inertia of the disk. Plus the child. Plus the inertia of the child. This is going to be 1/2 m. It's going to go ahead and make both of them little r. mr squared. And again, the radius is just the r, whether it's capital or lowercase, is going to be the radius of the merry-go-round. Okay. So we can pull out of this, we can pull r squared. So we're going to have 1/2 m mass of the merry-go-round plus the mass of the child, r squared. We want to solve. We want to try to solve to this point because again, we're working on learning to model the the world around us mathematically. And one of the things you do in mathematics is you're really not done with your derivation until you've simplified things as much as you possibly can. Now, let's go ahead and plug in our numbers. Let's make that a square bracket. I've already annoyed the mathematicians today. It's not trying to do it any further. We have 1/2. So the mass of the merry-go-round is 160 kilograms. And then the mass of the child, 18.4 kilograms. And on the outside, the radius of the merry-go-round, 2 meters squared. And so then what we're going to get, the total moment of inertia will be 394 kilograms meters squared. So not too bad of a way to start off the chapter. Kind of a simple little calculation there. Alrighty, moving on. Let's look at an exercise. Modified version of an Atwood machine is a block flat on a surface being pulled by a mass hanging over a pulley. If the blocks are released from rest, find the speed of the blocks after they have moved a distance delta y in terms of M1, M2, I, R, and delta Y. Ignore friction. So we're not actually looking to calculate a number here. What we're looking to do is derive an equation. Okay, so let's go ahead and look at this abridged Atwood machine. All right, so we have the surface that one block is going to sit on. We'll just go ahead and put a pulley on here. Yep. So there's going to be mass 1. Then let's see, we're going to have, yep. Let's go ahead and connect this. So we're going to have the cord going over the pulley. There we go. So this will be mass 1. That's mass 2. And now we know that as this moves, it's going to move with the velocity in that direction. It's going to then move through a distance. Move through a distance delta y. And then our pulley we're going to have to take into account that this pulley has radius r and a moment of inertia. Okay. So we're trying to find V is what we're after. Okay, so we're going to look at potential energy first. Let's see, 2, which is for mass 2. Okay, so we're going to get a negative mg dot to y, because of course, if we know that our final position is going to be y equals 0 at the bottom, that'll give us a negative delta y, causing the whole thing to be negative. For mass 1, delta U is going to be 0, because mass 1 isn't moving up or down. All right, now, changing kinetic energy total is going to be the change in kinetic energy of the blocks plus delta K for the pulley. Okay, so that's going to be K final 1, mass K initial for block one, mass 1, final for mass 2, minus initial for mass 2, and then delta K of the pulley. We know all of our initials. Are going to be 0 because there's no motion starting out. So we'll say that, so then we have final kinetic energy for mass 1, V squared. And I'm just putting in V, I'm not putting in V1 or V2 because they're connected by a cable. And so whatever velocity one mass is moving, the other one is moving the same velocity based on the fact that they're a single system. Okay, so then there's the final velocity of mass 2 and then the potential energy of the pulley after it starts moving. Okay, there's our total kinetic energy. Now we remind ourselves that omega is V over R. So then this will give us 1/2 m1 squared plus 1/2 m2 squared plus 1/2 I V squared over R squared. And now what we're going to look at is the total energy of the system. Basically the work done on the system. Delta U plus delta K. Remember our delta U, oh, that's mass 2. So negative mass 2 G delta Y plus 1/2 m1 squared, 1/2 m2 squared. And then I'm going to make this one look a little different. I'm going to do I or R squared V squared. And this is a system in equilibrium, so there's no acceleration, constant velocity. Okay, now, so everything equals 0. So what I'm going to do is I'm going to take the potential energy and I'm going to move it to the other side of the equation. And then I'm going to factor out a 1/2 and a V squared from everything else. Okay, so it's going to give me 1/2. And I'm going to have M1 plus M2 I over R squared, V squared equals M2G delta Y. Alrighty? Now, from here, we'll solve for V squared. Okay, so that means we're going to multiply through by 2 and divide through. Well, that was awful. Going to divide through by that whole thing. And so that means our denominator is going to end up being M1 plus M2 plus I over R squared. Then our numerator will be 2 M2G delta Y. And then I'm just going to square root everything. So the speed at which our system is moving in the end is right there. And so as you notice now, we have velocity in terms of M1, M2, delta Y, I, and R. Just as we were asked for. Okay, the next thing we're going to talk about is the idea of torque. So basically torque is when a force is applied, it causes the system to move in a circle. Okay, so let's think about that. So let's just start and make a pivot point. We're going to give ourselves some kind of lever arm. And then we're going to say, well, I'm going to apply a force, F at some angle. Okay, now, one thing we want to start taking account of is the fact that our lever arm, or from our center of rotation, we're going to have a vector r, so a position vector, and then we want to know the angle between these two. Now, to be able to do this, we want to take account. I'm not calling it Fy this time. That upside down T means perpendicular. This is the perpendicular component of the applied force. We want to know where that's at to figure out where our angle is. And so our torque is going to be the position vector cross the force vector. And so this is a vector product. It's called a cross product. And so what we're going to get then is, so when we break this down, it's going to become RF sine of theta. In a previous lesson, we looked at the determinant form of the cross product, but we're just going to go for the simple form, the RF sine of theta here, and the theta is the angle between the two based off the position of the perpendicular part of the force vector. And so the F sine of theta here, if you look at this, so sine of theta here would be the perpendicular component over F. And so your perpendicular is going to be the magnitude of the force, sine of theta, which means that your torque is going to be R multiplied by the perpendicular component of the force. Now, again, when we really think about this, we're looking at the applied force and the swing arm and the angle between the two. So we could redraw that saying, I could put force there, put my swing arm there. Then, of course, theta is going to be the angle between the two of them. Another way you could look at this is through the perpendicular component of, the perpendicular component of the swinging pendulum, or let's kind of take a look at that. Let's redraw. We'll go ahead and say, okay, here's our pivot point. Now I'm going to draw, my R vector would go right along my radius of motion. Then I'm going to have an applied force. We'll go ahead and look at the components here again. There's that perpendicular component. We know that that's going to be the angle theta. Now, what if we drew a straight line through this force? Just going to keep it going backwards. And then what we want is you want a component of the position vector that's going to hit that line perpendicular. So something like that. And when we say perpendicular, that means that right here, that's a 90-degree angle. So what we have now is the perpendicular component of the pendulum. Or in this case, that's going to be the lever arm. So the lever arm is your perpendicular component of your swing arm. And then your line of action is the straight line that goes along the force vector. In this case, we could say, well, we also have to think that this angle here is also going to be theta, because from geometry, vertical angles are always going to be equal. And so now we could say, well, our lever arm is going to be R sine of theta. And in this case, now our torque would be the lever arm times the applied force. So we end up with the same formula for torque. But let's look at this in a slightly different way. Let's go ahead and put our pivot point. And put my swing arm here, my radius of motion or circular motion. And then this time I'm going to draw my force back this way. Okay, now where's the angle theta? Well, there's a couple of things we could look at. Okay, let's go ahead and I'm going to go ahead and finish off my line of action. And then I could say, well, I could do, I'm pretty sure that's not quite a right angle, but we're going to pretend I could do that and take uh, my lever arm, or now this is usually the way I do it. I just take a look and I say, well, where is my perpendicular component of force? And that's going to be the component that's perpendicular to the swing arm itself. Okay, so it's right there, which means that my theta is going to have to be right there. So a little practice and you get pretty decent at figuring out where your angle is. I always try to locate my perpendicular component of force and go from there. But you can use either the perpendicular component of force or the lever arm, the perpendicular component of the swing arm, or the radius of curvature. Radius of, yeah, the radius of circular motion. All right, let's take a look at this exercise. A person lying on an exercise mat lifts one leg to an angle of 30 degrees in the horizontal with an 89 Newton weight attached to the ankle. The distance between the ankle weight and the hip joint is 84 centimeters. What is the torque due to the ankle weight on the leg? Okay, so I just kind of started saying, well, let's just draw a little rectangle for your body. Then I'm going to put in a pivot point. And then the leg itself, I'm just going to draw that as my R vector. And then you can imagine, okay, so then at the end, you're going to have your ankle weight, and it is going to have gravitational force, m times g, and you've raised your leg. Let's see here. Now, if we think about our mass times gravity as our force vector, then of course our perpendicular r would go right along there. We'll just say, there's my line of action. So that means, okay, so I have that. I could also look for the perpendicular component of the force, and that's going to come perpendicular from the swing arm itself. All of this is telling me that right here has to be the angle that I want to use. However, I've raised my leg to an angle theta, so I'm just going to call that angle in there phi. We'll have to figure out what that is. Okay, so we know that the torque that we're looking for is going to be R, let's see, gravitational force here, m times g, sine of phi. Okay, well, this is a right triangle. And so if theta is 30 degrees, this is a 30, 60, 90 triangle, so phi has to equal 60 degrees. Okay, so then from here we say, well, torque due to the weight on the ankle. Let's see, it's 84 centimeters away, so that's 0.84 meters. And we'll talk about this. So I'm going to go ahead and put the gravitational forces as negative 89 newtons because it's pointing down. And then we'll have the sine of 60 degrees. This is going to give us a torque of negative 64.7 newtons times meters. So the Newton meter is the joules. So it's negative 64.7 joules. So you notice that torque has units of energy. Now, positive versus negative torques. I think it's going to be easiest to think of clockwise, counterclockwise motion. So if you think about it, this mass on the leg would cause a motion going around that way, which is a clockwise motion. In angular motion, clockwise motion is negative, counterclockwise is positive. So I would just look at your the forces that are causing the torque, see which way the rotation would be caused based off those forces. And if it's counterclockwise, it's going to be positive. If it's clockwise, it's going to be negative. All right, so let's take a look at work done by torque. So here you see the work done by torque is torque multiplied by the angle that you rotate through, delta theta. The power supplied by torque is torque multiplied by the angular velocity, omega. Okay, so let's start to think about that. We're going to give ourselves a nice large rotating object. Okay, and then we imagine that this is being pulled. So we'll just draw a little cord off of it and imagine it's being pulled. We're going to put our center there. We're going to get an angular velocity that way. And so let's start thinking about this. Okay, so we have the radius. Now we know that as this disk rotates, it's going to move through an angle delta theta. And then at each individual little point here, so where the radius touches, we're going to have perpendicular forces. If we go down to the chord, those perpendicular forces would end up looking like that. And you're going to try, and so then you would end up traveling through I'm going to go ahead and call it some distance d right now because we'll talk about what that distance is. The distance that that cord will lengthen by as you're pulling on it to rotate the system, you think back, we have this wonderful thing called arc length. And so that distance is going to equal the arc length that your object has rotated through. Okay, so let's start looking at the work done. So work, you remember, this one's a dot product, which remember is the force times the distance moved, cosine of theta. If we look between the perpendicular force and d down there on the chord, the angle is, so theta is 0. So cosine of 0 is 1, so that's force times distance. But we also remember that arc length is going to be r delta theta. And so that's going to give us force perpendicular r delta theta. And of course, then we remember that force times r equals torque. So the work done by torque is going to, the work done by a torque is going to be the torque itself multiplied by the delta theta that the object rotates through. Because what you're, I guess it's back up and just show every step. So we'll say this is going to be torque over r multiplied by r delta theta. There, that way we haven't skipped any steps. Okay, and so of course delta theta in this case is radians. So then we say, well, what about power? Okay, so remember that power, that's going to be force times velocity times the cosine of theta. So this time, we're thinking about one of these individual perpendicular forces, and we know that we have an angular velocity, but we also know at each one of these individual little spots, we have a linear velocity. And again, going that way. So again, you see that linear velocity and perpendicular force have an angle of 0. So that means it's going to be cosine of 0. So remember, cosine of 0 equals 1. So we can say this cosine reduces to 1. That's going to leave us the perpendicular force times the linear velocity. We remember that linear velocity is radius times the angular speed omega. And we remember that our perpendicular force is torque over r. So we can say that this is torque over r. And then V is r times omega. And so what we end up with is the power due to torque is going to be the torque multiplied by the angular speed omega. And so that'll get us to power due to torque. And I believe that, yeah, that gets us all caught up to where we need to be. So thank you, and we'll just continue on from here in class. All right, have a good day.